Now it is your turn. Let's do the lab exercises. You will build and test this chapter's operations and see one rule for every lab. Every program must free the memory it allocates. Lab 1. This is about 30 minutes. Your goal is to implement the full core set of operations and then prove they work with a small driver program. You use the same node struct from Chapter 9. First, BSD insert. It adds a key and returns the root. The root may be a new node, so you always return it. Next, BSD search. It returns a pointer to the node with the key, or null if the key is not there. Next, BSD min. It returns the leftmost node. That is the smallest key in the tree. Next, BSD delete. It removes a key and returns the new root. This one has the 3 cases we studied. And in order, it prints all the keys in sorted order. This is how you check your work. To test, build the tree from these 7 keys. 20, 10, 30, 5, 15, 25, 35. Search for 15, which is present. Search for 99, which is absent. Then delete 10 and print the in-order result. One tip to remember. Every insert and delete returns the root. So the caller must write root equals BSD insert of root in the key, and at the end, walk the whole tree and free every node. Pause here and try it yourself first. Try Lab 1 on your own first. When you are ready, let us look at one solution. The hardest function is BST delete, so that is the one we walk through in 3 parts. The function takes the root and the key to remove, and it returns the new root. First, the base case. If root is null, the key is not in this subtree, so return null and change nothing. Now the search part. If the key is less than root arrow data, the victim is on the left. So we delete from the left subtree and store the result back into root arrow left. Storing the result back is what makes the pointer rewiring work. If instead the key is greater, the victim is on the right. Same thing on that side. Once we fall past both of these, we have found the victim, and the 3 cases begin on the next slide. We have found the victim, case 1 first. If both children are null, the node is a leaf. We free it and return null, so the parent's link becomes empty. Case 2, first half. If only the left is null, the node has just a right child. We save that child, free the node and return the child, so it takes the node's place. Case 2, second half. If only the right is null, the node has just a left child. Same 3 steps on that side. Note the order these tests come in. The leaf test has to be first, because a leaf satisfies both one-child tests as well. If we get this far, the node has 2 children. Case 3. We find the successor, the smallest key in the right subtree. We copy the successor's key up into the current node. And this is the line that must not be skipped. We delete the successor from the right subtree, so its key does not stay in the tree twice. Then we return root, which now holds the successor's key. The output confirms it. After deleting 10, the in-order print is 5, 15, 20, 25, 30, 35. 10 is gone and the order is still correct. Lab 2. This is about 25 minutes and it is a reasoning task. You are given a tree and you must decide if it is a valid binary search tree. The key point is this. You must check every key against all of its ancestors, not just its immediate parent. To do this, write a function called isBSD. It takes the root in 2 bounds, a low value and a high value. It returns 1 if every key sits strictly between low and high, and both subtrees also pass with tighter bounds. You start the call with long min and long max, the widest possible range. This is why the parent-only check fails. Earlier in this chapter, a learning check showed a node that passes a parent test but still breaks the real rule. The fix is to tighten the bounds as you go down. The left call gets low and the current key. The right call gets the current key and high. Pause and try writing it. Try lab 2 first, then let's check it. The whole function is just a few lines because recursion does the work. The function takes the root in 2 bounds, low and high. It returns 1 for a valid tree and 0 for a broken one. The base case: an empty tree is valid, so return 1. This is the real test. If the key is less than or equal to low or greater than or equal to high, the tree is broken. Return 0. These 2 lines recurse with tighter bounds. The left subtree must stay below the current key. The right subtree must stay above it. Both sides must pass. On a valid tree, the function returns 1. On the broken tree, it returns 0. That broken tree is built by hand on purpose. A node with value 45 sits under 70 on its left. It passes the parent test, since 45 is less than 70. But it fails the real rule, because 45 must be greater than 50 to live in the root's right subtree. The tightened bounds catch it. Lab 3. This is about 30 minutes, and it is the challenge task. You insert the same set of keys in 2 different orders. Then you measure how much the insertion order changes the height of the tree. Write a function called height. An empty tree has height -1. Then insert the keys 1 through 15 in sorted order into one tree. Insert the same keys in bisection order into a second tree. Print both heights and compare them. Bisection order means you always insert the middle key first. For the range 1 to 15, you insert 8 first, the midpoint. Then you do the same idea on each half, 1 to 7 and 9 to 15. This is exactly how you build a balanced tree from sorted data you already have. Pause and try it. Try lab 3 first, then let's look. The height function is short, and it is a clean example of recursion. The function takes the root and returns the height. The base case: an empty subtree has height -1. This makes a single leaf come out as height 0, which is what we want. These 2 lines get the height of the left subtree and the height of the right subtree. Each is a recursive call. Then return 1 plus the taller of the 2. The 1 counts the current level, and the taller side decides the height.